To simulate human thought, conversational AI data must travel at speeds that test the physical limits of our network infrastructure. System architects measure this complete loop using a metric called end-to-end latency. It tracks the exact duration from the moment a user finishes speaking to the moment the AI begins to reply. Biology dictates the requirements here. If a response takes longer than 400 milliseconds, the human brain perceives the delay. The AI sounds hesitant and robotic, causing users to instinctively interrupt it. This 400 millisecond limit acts as a strict latency budget. Every computational step spends a portion of it. But for South African deployments, standard global setups route real-time media streams to primary processing nodes in Western Europe or North America. Before the AI model can even generate a response, the system must process the audio. Voice activity detection endpointing and speech-to-text transcription consume immediate portions of the budget. The remainder must cover the heavy computational listing, the large language model generating its text, and the text-to-speech engine synthesizing the final audio. When standard routing models attempt this pipeline from South Africa, they mathematically failed to complete the loop within 400 milliseconds. Upgrading to a faster language model or a more efficient software stack will not solve this delay. Achieving natural AI voice in this market is not a software problem. It is a strict physics and network routing problem that demands a completely localized topology. A packet sent from a business hub like Johannesburg to a European data center in London or Amsterdam must cross roughly 9,000 kilometers. That data is physically constrained by the speed of light traveling through glass fiber optic cables. This routing relies on massive submarine infrastructure, specifically systems like the West Africa Cable System and Google's Equiano cable. Equiano uses advanced space division multiplexing to achieve highly direct transmission, but the physical transit still requires significant time. The theoretical minimum round-trip time to Europe is 88 milliseconds, but real-world routing pushes this penalty to 175 milliseconds. Applying this to our latency budget, subsea transit instantly consumes nearly half the available time. We still have to process the audio. Applying standard delays for voice activity detection and speech-to-text transcription pushes the total dangerously close to the absolute 400 millisecond limit. At this point, the language model has not generated a single token of text, making it mathematically impossible to synthesize and return an audio response in time. To make conversational AI viable, enterprise architects must eliminate the international subsea transit step entirely. Subtracting a 170 millisecond transit penalty from a 400 millisecond budget leaves insufficient computing time for modern inference engines. The entire architecture must be redesigned. The solution requires terminating the entire SIP trunk signaling and media pipeline locally inside South Africa. A call begins with a local user initiating contact over a domestic mobile carrier, like Vodacom or MTN. Traveling over local LTE or 5G cellular networks, this domestic network transit costs only 28 to 35 milliseconds of round-trip time. Instead of routing to the open internet, the carrier forwards the call to a carrier-neutral co-location facility, such as Terraco's Isando campus in Johannesburg. Inside these facilities sits NAP Africa, the region's largest internet exchange point. Here, telecommunications providers and cloud platforms peer directly, keeping traffic completely off the public internet. The final connection bridges the gap. The system uses a virtual cross-connect over the Africa Cloud Exchange to link directly into local cloud on-ramps like Azure. Benchmarks show this cross-connection processes in under 2 milliseconds. This 2-millisecond local hop replaces the 170 millisecond penalty of routing to Europe. By cutting out the subsea journey, the system reclaims roughly 168 milliseconds of time. Peering directly at a local internet exchange point bypasses international internet routing entirely. This provides the massive temporal headroom required for complex language model reasoning. Reclaiming 168 milliseconds of transit time is only useful if the local cloud infrastructure can process the AI models fast enough to capitalize on it. This requires deploying high-density compute hardware locally, such as Azure's NCH100 virtual machines within the South African region. The critical metric for evaluating this hardware is time to first token. This tracks the exact duration it takes the language model to begin generating its response. Serving frameworks dictate this speed. Standard frameworks yield higher delays under load, but highly optimized inference engines like TensorRT LLM can push the time to first token down to roughly 100 milliseconds. Returning to our latency budget, we stack the newly optimized components: 30 milliseconds mobile transit, a 2 millisecond cross-connect, 30 milliseconds for speech-to-text, and 100 milliseconds for TTFT. Finally, a raw speed text-to-speech layer adds 40 milliseconds, settling safely below our absolute limit. Bypassing subsea cables and running optimized inference engines on local H100 GPUs solves the baseline latency problem. Solving baseline latency does not guarantee survival in production. South African deployments face a unique physical threat: rolling power grid instability, known as load shedding. During prolonged municipal power outages, cellular towers lose primary power and drop from 5G to legacy 4G or 3G fallback modes, violently disrupting data flow. This chaotic variation in packet arrival times is defined in network engineering as jitter. Traditional voice-over IP systems use fixed jitter buffers. Under these conditions, they are fatal. They either add unnecessary static delay, or they run completely dry when the network stutters, dropping the audio entirely. To counter this, engineers strip out standard SIP audio handling and implement WebRTC's NetEQ, a highly adaptive jitter buffer. NetEQ dynamically analyzes network ticks every 10 milliseconds. It microscopically accelerates or stretches audio playout, faking a continuous stream to hide the network delay. This is paired with Opus Deep Redundancy, or DRED. DRED actively synthesizes up to 1 second of dropped packets directly at the decoder, without increasing the physical holding time of the buffer. Terraco-peering fixes the lost speed. But it is the combination of NetEQ and active packet synthesis that protects the fragile conversational state from the physical realities of the local power grid. When configuring the final production environment, architects face a choice between two distinct pathways. The maximum consistency pathway prioritizes audio fidelity, resulting in a total round trip of 480 milliseconds. The alternative is substituting in prioritized speed layers for the ultra-speed pathway. By prioritizing raw generation speed in the synthesis layer, the ultra-speed pathway successfully achieves a deterministic 360 millisecond turnaround. At 360 milliseconds, the system safely clears the biological threshold, ensuring the human caller perceives the AI as responsive and naturally conversational. Real-time AI voice in South Africa cannot be achieved in a software silo. It demands an uncompromising, unified architecture, bridging local telecom peering, direct data center cross-connects, and bare metal edge compute.